All right. So because we had 2 days campus closure, so then I propose postpone the homework 3 due day, like 2 days extension on that, and then also we'll have exam 1 on Wednesday then next week. Okay, there's still a little bit of the content we need to cover today for both homework 3 and then exam number 1. Okay, so that's why they are postponed. Um, Also for the lab, so we canceled lab yesterday. For you guys in yesterday's lab section, if you want, you can do the lab tomorrow afternoon. Okay, so if your schedule allows you, and then also you want to do it that. Otherwise, we'll make it up in one of the makeup weeks. Okay, it's the same 2:10 to 5:30. Okay. Um. Now, if you want to come a little bit later, like 3 something, I think you still have time to finish this one. Because this one is a simple one. It takes about 2 hours to finish it. Okay, so if you want to come in tomorrow, that's fine. But let me know so I know like if we have like 6 setups, so we can have like 12 people or so. So that means I can take like 4 of you guys. Okay, so then this will be like first come first serve. So just send me email um, that you want to come. So then we'll do that. Okay. Otherwise, you can make it up in one of the makeup weeks. Okay. All right. So, and then let me see. Now in principle, you guys can come in, let's see, Friday afternoon, because I have other section here, but they are 9 of them. So I can probably like take 2 more groups there this Friday. Okay. All right. But yeah, just let me know if you want to come. Okay. um, Oh, let's do this way. So from next week, then let's just move it. If you guys are not making it up, so then next week come back and we'll be just doing this week lab. Okay, the ideal guess law for Tuesday section. Okay, for Thursday section, you guys fine. Okay, so just go with schedule. So then, for Tuesdays, we are kind of like 1 week behind schedule. Okay, so we'll do it that way. Okay, all right. But still, if you want to come tomorrow, let me know. You can still do that. Okay. Then next week, you don't have to come on Tuesday. Okay. All right. For classroom disinfection, Anthony and Joshua today. Okay. So today we'll be finishing up chapter 2, and then we probably will check chapter 3, like maybe 1 or 2 sections there. Okay. So let's check. So last time we talked about the ideal gas. So 2 assumptions here need to be made before we actually are talking about ideal gas. So one is we treat them as point particles, so their volumes doesn't matter. Second, we treat the distance between them, each of the 2 atoms or molecules, to be far away from each other. So there's no interaction that you need to consider here. Okay. Under those 2 assumptions, then we can treat the ideal gas system as ideal gas. So the conclusion is for ideal gas, you can write the equation to relate the quantities that describe the ideal gas. So PV equal to NKT. All right, so where N is the number of the molecules, and then K is the Boltzmann constant. P is the pressure, V is the volume, T is the temperature. Okay, you can write it in another way by using the Avogadro's number, and then small n as the moles of molecules. So in that sense, you can write PV equal to small n times R times T, as the equation shows down here, where R is the gas constant, which is 8.31, joules per mole per Kelvin. Okay, so that's the ideal gas law. Two expressions, basically they're the same. For the first order approximation, so that means if you have to consider the volume of the gas molecules or atoms, as well as the interactions between them, so then you need to introduce two terms here. So this is for the accounting the interaction between gas molecules. This is for the volume of the gas molecules. So then this is rewritten as the van der Waals equation as the equation of state. Okay, so P plus this term times V minus this guy equal to nRT. Okay. All right. So today we'll be looking at pressure, temperature, and the RMS speed, which means the rule means square speed. Basically, you take squares of the speed, and then you actually square the speed, and then take the square root of the average on that term. Okay, but basically, this is the kinetic theory, which relate the microscopic quantities to the macroscopic quantities. Okay, so for microscopic quantities, that means position velocity of each individual atoms or molecules. Okay, so these quantities describe the microscopic um, aspect of the each individual molecules. Okay, however, for like pressure and temperature, all right, so those are macroscopic quantities, which means the quantity that describe the collective behaviors of the gas as one whole system. Okay, so let's see what are the relationship between the microscopic quantities and then the macroscopic ones here. Before we are going into details, we are going to make a few assumptions here again. So the first assumption is we are going to assume all the molecules are identical. So they're all the same. All right, they have the same mass. All right, and then we are going to treat them as, again, point particles. All right. The second assumption is molecules move randomly, and always you can describe them as Newton's law. So that means Newton's law will apply when you are describing those quantities, positions, velocities, force, etc. We are going to assume the third one is the collision between molecules and the walls. They are elastic. So that means when there's collision happen, there's no loss in kinetic energy. Okay, so the energy is still conserved here. So those three assumptions. All right. So basically, for an ideal gas, if you can treat a system of gas like a collection of gas as ideal gas, then so we are ignoring the interaction between the gases. That means the molecules. So then we are not considering the collisions between gas molecules here. So the main thing here you want to, or the main event here you are looking at is the collision between molecules and the walls. Okay, so let's say this is one wall of the container, and then you have a molecular of gas that hits the wall and then bounces back. Okay, so during the collision, we are going to assume kinetic energy is conserved. So then that means this guy. So then pretty much it says this, because the wall is a big one, this is a small one. So that pretty much says if you have V, velocity V comes in, say a certain magnitude, say 5 meters per second or maybe 500 meters per second, it will come back as 500 meters per second, right? That's the elastic collision. So then there's no loss in energy over here. All right. But during the collision here, because there will be probably like direction change of the velocity of the molecule here. So then there's momentum change, okay? M times V will be changed. So then it received the impulse from the wall here. At the same time, it will give an impulse to the wall, okay? Or the force to the wall, okay? So then for each collision that happens, the wall will receive a certain force from the molecule, right? Now, if you divide the force by the area of this wall, then that gives the pressure of the wall by this single molecular. Okay, so when a collision happens, there's pressure exerted on the wall. Now we are going to look at this event in just one dimension, okay, in the x dimension, and then we are going to expand that to y and z directions, okay? So let's assume that there's a molecular here goes to the left side of the container. So the simplest scenario here, you can assume this is a cubic container, okay, which each side is L in length. So what happens here when it hits the wall at this moment, it will bounce back, okay? So the velocity, the speed will not change, the direction changes, okay? So then you have incoming momentum for the molecular to be this guy. If you take to the right as positive, so then the initial momentum will be negative, okay, in x direction. The final momentum then is positive, mvx, okay? Vx is the same because it's elastic collision, all right? So then the force exerted on the wall here should be equal to the momentum change, right? Or the impulse being delivered to the molecular here. So momentum change divided by the time t, okay? So let me put this way. You can write down here. Somewhere here. So I'm not blocking the figure there. So the force, it's going to be equal to the momentum change of the molecular divided by the time t, the impact time, right? Now, how long does it take for the collision to happen? Okay, so from the first time to the next time. So the delta t here, when it hits here, it will bounce back, right? It will travel this distance L and then hits the wall and then come back, right? So that's how often the collision will happen. Or you can think about that as the average time for each collision, all right? So then it's a round trip going from here, bounce back. So delta P, we know it's going to be just mvx, the final minus the initial, mvx minus that one, right? Delta T then will be twice of L divided by the speed Vx, okay? So that's the force, right? Now this will be twice mvx divided by 2L divided by x, so x squared on the top, okay? So then force is equal to mvx squared divided by L, okay? So that's where this term is coming from, okay? So this is where this is equal to F, that's because of that, okay? So mvx squared divided by L, all right? Now the area, the force divided by the area will give you the pressure by a single molecule, okay? So the area, if we consider this as a cubic container, then each wall has the area of L squared, okay? So that's L squared there. So then pressure by a single molecular is equal to mvx squared divided by L to the cube, because this L in the numerator here, it's actually under denominator of numerator. So then it goes down here to the L to the Q. Now L to the Q should be the volume of the container, right? Because it's a cubic container. So then that's equal to V. V stands for volume. Capital V stands for volume. Small v stands for velocity or speed, okay? So pressure exerted by a single molecule on the wall is equal to mvx squared divided by V, okay? So that's what happens for a single molecule. All right. So this guy, so this is what we get from the previous slides. Okay. Now for a box of gas, that's assuming there's n molecules. So then overall pressure of the gas system should be the same as the pressure the wall is experiencing, right? That's equal to n times the pressure by a single molecular. Okay, so then that's equal to n times mvx squared divided by v. Okay, volume v, on the top v here is the speed. Okay, all right, so then p equals to this, right? So you move v to the left hand side of the equation, it becomes p times v equal to n times the mass times the vx squared. Okay, so now you are going to do a trick here. You multiply by 2 on the right hand side before n. Now after n, you put 1/2. So basically that cancel out, but that's the trick you are playing here. Okay, so that gives you 2 times n times 1/2 mvx squared. Okay, we want put 1/2 here because then this is the kinetic energy of the gas molecular because it's 1/2 mv squared. Now in the x direction, okay? And we should just do the average of that, okay? So because each molecular might have a slightly different speed from one to another. So we are actually should be talking about the average speed of the molecules, of the gas molecules, okay? All right, so then P pressure times the volume, these two are the macroscopic quantities, okay, related to the microscopic quantity, which is the kinetic energy of each single molecules, okay. All right. So from there, if you compare to the ideal gas law of PV equal to NKT, all right. Now to match up the 2n here, we put 2 in front of n here, but we put 1/2 after n. So then 1/2 n or 2n times 1/2 kT. All right. So PV is equal to this guy. PV is also equal to this guy. So you compare these two expressions, then it will come to a conclusion that 1/2 mv squared is equal to 1/2 kT. Okay. So that means kinetic energy of single molecular on average is equal to 1/2 times K, which is the Boltzmann constant here, times the temperature of the gas system, okay? So the temperature is the macroscopic quantity. Now the velocity is the microscopic quantity, okay? So these two are related now, all right? So for kinetic energy in one dimension is simply 1/2 kT. Now we can expand this conclusion into other two dimensions in y and z. Okay, so pretty much if you are talking about the averages, so then there should be no reason that y and z should be different from x. Okay, for the average. So the averages should be equal to each other. Okay, in x direction, in y direction, and in z direction. So the overall kinetic energy of the gas system for a particular molecular should be 1/2 mv squared, which means the x component square plus y component square plus z component square. Okay. Each component is 1/2 kT. So then 3D in 3 dimension, 3 components should add up to be 3/2 kT. Okay. So average kinetic energy for a molecular should be equal to 3/2 of kT. All right. And for a gas system, this is we'll be talking about this internal energy of a thermodynamic system in the next chapter. Okay, but basically I'm going to throw this right away so then you guys, when we talk about the internal energy in the next chapter, we know that it's going to be just equal to 3/2 of nkt. Okay, because each molecule is 3/2 of kT, then the system of gas is 3/2 times n times kT, where n is the number of molecules in that collection of gas system. Okay, so internal energy is equal to n times the kinetic average of each molecule, which is equal to 3/2 nkt. or 3/2 nRT. Okay. Now this is only valid for ideal gas, because for ideal gas, we are ignoring the interaction between the gas molecules, right? So then the internal energy is only determined by the temperature. If you are talking about a real gas system where you are considering interaction between molecules, or maybe between atoms within a molecules, then the internal energy is slightly different. Okay, we should add those terms later on. But for right now, if you are dealing with ideal gas, then we are not considering other energies. We are just considering kinetic energy. Okay. All right. So in that case, kinetic energy average is equal to 3 kT. So then if you take square root of the speed square average, which is called the root mean square speed of a molecule, okay, should be equal to then just square root of this guy, okay, because it's equal to 3 kT if you write in terms of R and capital M, which is the molar mass, all right, of the gas molecule. So then this is equal to square root of 3RT divided by M. Okay, where R is the gas constant 8.31, and then mass, the molar mass, capital M is molar mass. Okay, so this is typical like for hydrogen is 2 grams per mole, but we should use kilograms per mole. Okay, so when you look at molar mass, they are pretty much given in grams per mole, but you want to convert into kilograms per mole. Okay, if it's not in that unit. This root mean square speed can be also be written as 3 kT divided by mass, small m, which here small m is the mass for each individual molecule. Okay, so if you use that, because k is a small number, m should be also a small number. So that's the molecular mass in kilogram. So this should be a small, pretty small number. Okay, much smaller than this guy. Depends on what's given. You are going to pick either this one or that one. Okay, one of those two expressions. Okay. All right. Now this is only for kinetic energy. Okay, so again, as I mentioned, if you are considering like if this is a compound molecule, say made of 2 atoms or more, then there's probably like vibrational and rotational energies, okay, involved. Okay, so if um yeah, I don't remember if this is been mentioned in general chemistry, but if it was, so between two molecular atoms of a molecular cell, there's this vibrational position change, and then also like rotational. Okay, those are energies as well. But yeah, so for right now, we'll just focus on kinetic energy here. All right. So let's take a look on the first example here. This says 1 mole of argon gas is confined to a 1.0 liter container at a pressure of 10 atm. What's the RMS speed of the argon atoms? Consider the argon gas to be ideal gas. Okay, so for ideal gas, then ideal gas law will apply. And 1 atm is equal to 101,325 pascals. Okay. So you also need a constant, you also need the molar mass for the argon gas. Okay, so you can look it up, but I'm going to just give you that constant here, which is capital M. Okay, capital M for argon is equal to 39.95. This is in grams per mole. Okay, so as I mentioned, you should convert into kilograms per mole. Now, you can treat it as ideal gas, so PV equal to nRT will apply here. Okay. V of RMS should be equal to square root of 3RT over M, or 3KT over M, small m. From liter to meters cube, 1.0 liter is equal to 10 to the minus 3 meters cube. Oh, actually, yeah. These two numbers are given here, so oops. For argon gas, the molar mass, and then for helium, molar mass is also given there. All right. So let's see here. So VRMS is equal to 3RT over M. Okay. We know M. I don't think we know T. Okay. It didn't tell us T, but it tells us P and V. Okay. P and V and then M is 1 mole. Okay. So then R and T is equal to, so if this is N is equal to 1, so then PV equal to RT. Okay. Because M equal to 1 mole. So then it tells us P and V, so you can use P and V here instead of RT. Okay, so V of V RMS then should be equal to square root of 3 PV in this case because of that. Okay, divide by capital M. Okay, so then 3 times 10 ATM. Okay, now you want to do the conversion here because ATM is not SI unit. Okay. Also, V is 1.0 liters. That's not SI units. So minus 3 meters cube over liters. Okay, that's the conversion there. Divide by the mass, 39.95. That's in grams. So you want to convert it into kilograms. Okay, per mole. After that, you're going to take square roots. Okay. So then VRMS is equal to 276 meters per second. Okay. Roughly 2.8 times 10 to the second meters. Now, the second part is asking you to compare this to the helium. So let's take a look at helium. For VRMS of helium, so you can say it that way, it's RT, but under the same condition, so RT will be equal to PV. Okay, so 3 times of PV over, now this time, molar mass for the helium. Okay, so the same on the top, 3 times 10 times 101,325. And then 1.0 times 10 to the minus 3. Okay, the same there. I'm dropping the units here because they are already converted into SI unit. For helium, it's 4.003. Now this is minus 3. Okay, that should be in kilograms per mole. So for helium, it's 871 meters per second. Okay, or roughly 8.7 times 10 to the second for the speed, right? So you can see argon is heavier than helium, but then its root mean square speed will be less, okay, because it's inversely proportional to the molar mass, square root of the molar mass, okay. Any questions you guys might have? All right. So if that's clear to you, we can move on here. So if you have a mixture of gases, so for example, air is a mixture, the two major components of air is oxygen and nitrogen, plus other like small components of other gases. But this is about oxygen about 21%, nitrogen makes about 78%. Okay, so those two make up like 99% of the air. So for a mixture of give different gases, the total pressure comes from the contribution to the components like the oxygen and nitrogen here, the two main components here, okay? So you are going to assume just each component will take up the whole space for the volume, okay? So you take the overall volume And then calculate what would be the pressure exerted by, say, oxygen and then nitrogen, and then you will add them up to be the total pressure. Okay, so this is called Dalton's law, or also called Dalton's law of partial pressure. So basically, it's proportional to the fraction of the um, molecules, number of molecules. Okay, so for two gases, you have total pressure equal to P1 plus P2, where P1 and P2 are proportional to their numbers of molecules. This is in moles. Okay, it could be also in just number of molecules, capital N. All right. Now let's consider collision between molecules. Okay, so we start with collision just with the walls. Now let's take a look on the collision between molecules. So say if you have a collection of gas here. Now, so this is the for one molecular of gas here. So we are going to assume this is a sphere one. Okay, so probably like one single atom molecular to be the case here. Assuming it goes in, say, in time t, a certain time t, it will travel then the distance of v, average v times t. Okay, that's how far it will travel. And then, so if this guy is colliding with a second or third molecules here along the pathway here, radius for this molecular is R1, and then for other molecular is R2. So then you are not looking at only this path in the red, but also considering adding the radius for other molecules up. So then you are looking on this one in black over here. Okay, so that's the total volume. All right. So then in that volume area, it will collide with other molecules. All right. So assuming that there's m sub v of molecules per unit volume, so this is molecules per unit volume, then the average distance traveled by a molecular between collisions, okay, should be equal to, right, the total length traveled by divided by the number of molecules at the bottom here. So at the bottom here, this is the number of molecules, okay? So this is molecular per unit volume. Now pi d squared times Vt, Vt is the whole length. So this is the volume, okay? This whole thing here, pi d squared Vt is the volume. It's cross-sectional area times the length, okay? So that's the volume. And molecules per unit volume times volume, that gives you number of molecules here encountered. Okay, so then the total length Vt over number of molecules encountered should be equal to the average distance traveled by a molecule before it hits the next one. Okay, so that's called lambda. It's called the mean free path. So that means it can travel on average travel that distance without hitting another molecule. Okay. Now for a pure gas system, okay, so then R1 will be equal to R2 because then each molecule will have the same radius. Okay, so we are starting just with in general, you could have like different gases, but if you have pure gas, then R1 equal to R2 equal to R. So then in that case, D is equal to 2 times of R. So D squared will be equal to 4 times R squared. Oh, actually, I think I forgot about this line here. So this is from the assumption we had earlier here, but in real scenario, so we are assuming here in this case, the other molecules are stationary, right? In real scenario, other molecules will move as well, okay? So your chances of hitting a molecule when it's stationary now compared to when it's moving, right? So chances higher if other molecules are stationary, but if other molecules can also be moving, then the chance is smaller, okay? So then you have a square root of 2 factor over here to account that, okay? So it becomes square root 2 of v mv pi d square. Now if d equals to 2R, so then D square equal to 4R, so then this mean free path becomes V, or it becomes, actually there are two steps here. So you also write MV as capital N, total number divided by the volume. All right, this is total number of the gas molecules divided by the total number of the volume. Okay, so then volume can go up because it's the denominator in the denominator, it becomes numerator. So 4 comes from 2R squared, where's the D squared? Okay, so 2 squared becomes 4. So 4 square root of 2 times pi R squared times N, the total number of molecules for the gas. Okay, so then it becomes this equation here for the mean free path. If you have ideal gas, then you can substitute V over N with KT divided by P. Okay, that's because PV equal to nRT. All right, so it starts out so from PV equal to nRT there, or NKT in this case, PV equal to NKT. All right, so then you move V to this side. All right, you move this two term to the other side. So then N over V is equal to P over KT. Or we are looking for V over N, so then it's the other way around. So V over N should be equal to KT over P, okay? As the slide shows there. So replacing N over V with KT, then it becomes KT divided by 4 pi square root of pi R squared divided by P, where P is the pressure, okay? T is the temperature, all right? K is the Boltzmann constant, and R is the radius of the molecular, gas molecule, okay? So this is the mean free path. The term associated with this is called mean free time. That means on average, how much time it takes to hit the next molecule, or on average, how much time it can be free without hitting a molecule, okay? So then this is the average distance should be divided by the average speed, which is usually usual choice. This is the RMS speed. Okay, so V here comes down here. So then mean free time equals to lambda over V RMS, okay, which is KT over 4 square root 2 of pi R squared. All right. So let's take a look on the example here on engineering application. So it says state of art vacuum. So that's the currently probably the best vacuum you could have, can attain pressures as low as 7.0 times 10 to the minus 11 in Pascal. Suppose that the chamber contains helium at this pressure and at room temperature of 300 K. Estimate the mean free path and the collision time for helium in the chamber. So you're looking for mean free path and mean free time, okay? Lambda and tau in this case. So it will be the two equations we had in the previous slides. Lambda equal to KT over 4 times square root times pi times R squared times divided by or times P here. For K it's 1.38, okay, times 10 to the negative 23 joules over moles times Kelvin. And you have the rest, or not exactly, you have diameter, so which means 2R as 1.0 times 10 to the minus 10. Okay, so then R should be 1/2 of that. And then you are going to look at what would be tau, which means lambda divided by VRMS. Okay, VRMS can be calculated using the equation of square root 3RT divided by capital M. For helium, this is 4.003 in grams per mole. Okay, I think that's all you need. Of course, R is 8.31. All right, so I think we are just putting numbers in here. 1.38 times 10 to the minus 23. So if we put everything in SI unit, I can just leave out the unit. 300 Kelvin, that's in SI unit. Okay, so 300. 4 times square root 2 times pi. This guy would be 0.5 times 10 to the minus 10. Okay, and then remember you need to square that term, and pressure is 7.0 times 10 to the negative 11. Okay, so if you have everything in SI unit, it should be about 1.33 times 10 to the ninth power. Okay, and for this one, you want to calculate what's this first. Okay, so this is square root of the rule mean square speed 3 times 8.31 times T 300 K in Kelvin divided by helium 4.3003 times 10 to the minus 3, okay, in kilograms per mole. So that's 1367 meters per second. And then take that over here, 1.33 times 10 to the ninth, divide by that meters per second, which would be about 9.73 times 10 to the fifth second. Okay, so pretty much you don't see another helium, okay, like in quite a long time. Okay, all right, any questions you guys might have? So we only have 5 minutes remaining. I think we'll just stop here then for today. Okay.